Welcome everyone. In this part, I will discuss about method to measure absorption coefficient and applications of acoustics, that is designing of hall for speech, concert and opera. In my previous lectures, I talked about acoustics, its properties and its importance, reverberation time, Savin's and Eyring's formulae on reverberation time, absorption coefficient of sound. So there are actually different ways to measure absorption coefficient of sound. Here we will talk about, or I will discuss, three different ways to measure absorption coefficient. So the first one is a reverberation chamber method. In this case, first we will measure the reverberation period of room with any absorbent materials. Then the absorbent materials are removed and the extent of the open window is gradually adjusted until the reverberation time is the same as before. Now the ratio of the area of window open to the total area of cushions or other absorbent materials is then determined and considered as absorption coefficient of the substance. Now for the reverberation chamber method 2, first we measure the reverberation time without absorbing material, that is, in that case T1 is equals to 0.161 into V divided by alpha into S, that is the summation over alpha into S, and this is actually the total absorption. And then we measure the reverberation time with absorbing materials and we denote this as T2, and T2 is equals to 0.161 into V divided by summation over alpha into S plus alpha M into Sm, and this is actually for the absorbing materials. Now the absorption coefficient alpha M, you can actually find this by subtracting T1 from T2, and in that case alpha M is equals to 0.161 into V divided by Sm into T1 minus T2 divided by T1 into T2. Now for the reverberation chamber method 3, this is the third method to measure the absorption coefficient. So here the average value of the absorption coefficient of a room may be calculated by the concept of decay of intensity. Now according to the concept of decay of intensity, when we switched off the source of sound, the intensity I at T is given by I is equals to Im into e to the power minus C into T, where C is equals to alpha into S into small v divided by 4 into capital V, where alpha is the absorption coefficient, S is the surface area, this small v is the velocity of sound, and this capital V is the volume of the hall. So let's say two different sources of sound are placed one by one in the hall, and Im and I dash M are the maximum intensities for two different sources. Now if T1 and T2 be respectively the times for these intensities to fall to the threshold intensity of sound, then you can say alpha, that is the absorption coefficient, is equals to 0.05 into V into ln, that is the natural log of Im minus the natural log of I dash M divided by S into T1 minus T2. When we use 0.05 here, so in this case the length is in feet, but when we use 0.161 here, in that case length is in meter. Now I will discuss about applications of acoustics, that is designing a concert hall. Acoustically good hall means that in which every syllable or musical note reaches an audible level of loudness at every point of the hall and then quickly dies away to make the room ready for the next syllable or group of notes. Now to build or design a concert hall, we need to know the desirable acoustics properties of the hall. So one is even dispersion. And evenly dispersed with no prominent echoes, no significant dead spots or live spots in the auditorium is actually more pleasing. A feeling of intimacy or musical presence is required. That means listener felt more a part of the performance and not isolated from it. One physical factor which has been correlated with such preferences is the time between the direct sound and the first reflected sound which reaches a listener. Good projection of the sound is required. A good auditorium will achieve effective projection of the sound to the rear of the auditorium so that those distant listeners will not experience the extreme loss of the sound level caused by the inverse square law. To do this, you would need a sufficiently long reverberation time. A good clarity and articulation is actually required. Basically, the richness and fullness added by auditorium reverberation is desired. Nevertheless, such reverberation decreases the clarity, that is the clarity of articulation. So, fullness and richness work against the clarity. And you would need to think about a reasonable reverberation time by an appropriate compromise of clarity versus fullness. A long enough reverberation time but not too long reverberation time is actually required. A very good balance of low and high frequencies is required. A proper balance of high and low frequencies of sound is usually a matter of boosting the bass. If the auditorium has a short enough reverberation time that approaches the inverse square law, then the bass loss problem is encountered. In most cases, the problem is partially overcome by having reverberation time for low frequencies which is longer than that for the high frequencies. And the last but not the least is the noise and the sound insulation. In a good hall, no noise should be reached from the outside. Noise may be defined as the unwanted sounds. For instance, outside noises are street traffic, hammering, drilling, operating machineries, moving of furniture, electrical generator, etc. From the inside, you can think that noise comes from the machinery, typewriters, mobiles, projectors. So basically, for a good hall or for a good concert hall, you need a very good sound insulation. So now, if you think that the first two, that is the event dispersion and the feeling of intimacy or the musical presence, is actually related to the shape and the surface of the hall, and the good projection of sound, good clarity, long enough reverberation time, and the good balance of low and high frequencies depends on the control of reverberation time. And the last point is the sound insulation. So when we design the concert hall, we need to work on the shape and the surface of the hall, on the reverberation time and the sound insulation. So now, coming to the shape of the hall, there are actually three factors of the shape. So one is the internal shape, second one is the surface and the ceiling, and the third one is the floors. Concerning the internal shape, a rectangular shoebox shaped concert halls with stage across one narrow end is excellent for music. And for the greater seating capacity, the side walls should be splayed from the stage, and that is actually in between 30 to 60 degree. Now for the surface and ceiling, we need to avoid round walls, that is circular or any elliptical shape, because such walls concentrate the reflected sound in particular areas that leads to a non-uniform sound intensity in the auditorium area. We need to avoid strictly parallel plane walls like those in the halls of a strictly rectangular shape, because standing waves with a highly non-uniform sound intensity, that you can think about nodes and antinodes, can be formed between such walls. So in general, angled side walls spread the sound energy and contribute to even dispersion. And normally, like this picture, ceiling reflectors, or which we actually say clouds, are used to direct the sound energy from the stage to the sitting areas. In some cases, clouds are made absorptive to avoid late reflections. Also in some cases, we actually cover high ceilings with absorbent materials to avoid echoes. Now for the floor, a sloping floor is actually favorable for a very good auditorium. In general, the sloping of the floor of a good auditorium should not be less than 8 degree. Now to avoid echelon effect, we need to cover the floors with carpet. So basically, the process of combination of multiple echoes and forming a new sound is known as echelon effect. A set of railings and rectangular surfaces is said to produce that effect. So now the second point is how we can control the reverberation time. By providing windows and ventilators can be opened and closed to make the optimum time of reverberation. We need to use heavy curtains with folds. The walls are lined with absorbent materials such as felt, fiberboard, glass wools, etc. We need to have a full capacity of audience. Also, we need to cover the floor with carpets. Now, for a broadcasting room should be practically have no reverberation. It entirely be covered with porous materials to have almost 100% absorption. With large absorption, the time of reverberation will be smaller, which will minimize the chances of confusion and may go below the level of intelligibility of hearing. Therefore, sufficient loudness in every portion of the hall is an important factor for satisfactory hearing. The loudness can be maintained at desired level by using large sounding boards behind the speaker and facing the audience, large polished wooden reflecting surfaces immediately above the speakers. Low ceiling are also useful in reflecting the sound energy towards the audience by providing additional sound energy using more number of speakers. Now, the last but not the least point is the noise and sound insulation. So we need to avoid opening of pipes and ventilators. We need to allot suitable location for doors and windows. We need to use heavy glasses to doors and the windows. We have to provide double wall construction with airspace between them. We can actually do the sound insulation by interposing layers of some acoustical insulators. We can use some soft floor finishing, that is, we can use carpets or rubbers. Also, we can insulate the machines, like we can insulate the refrigerators, lifts, typewriters or the projectors. Also, what we can do, we can construct a small soundproof cabin for machines and office staff, and certainly making the hall soundproof. So in this way we can actually exclude the noise or the sound from outside. So that's all about acoustics, and in my next lecture I'll talk about ultrasonics.